Think about a baseball being hit by a bat. The bat and ball are in contact for only a tiny fraction of a second. But during that short time, the ball's motion changes dramatically. That is the situation where impulse becomes useful. In many collisions, the force is not constant. It rises quickly, reaches a large value, and then drops again. Instead of trying to track the exact force at every instant, we often describe the overall effect using impulse and average force. In this video, we will connect force, time, and momentum. We will see that impulse is what changes an object's momentum. Then we will use that idea to analyze a steel ball bouncing off a hard floor. There are many situations where the force on an object is not constant. A collision is one of the best examples. When the bat first touches the ball, the force may be small. As the ball compresses and the interaction becomes stronger, the force increases. Then, as the ball leaves the bat, the force decreases again. The graph on this slide shows this idea. The vertical axis is force, and the horizontal axis is time. The actual force changes during the collision, so it forms a curve rather than a flat line. To simplify the analysis, we use an average force over the collision time. The average force is not saying the force was actually constant at every instant. It is a single constant value that would produce the same overall change in momentum during the same time interval. The area under the force versus time graph represents impulse. A large force, a longer contact time, or both can produce a larger impulse. That larger impulse means a larger change in momentum. Now we can define impulse mathematically and connect it to momentum. From Newton's second law, the net force is related to how quickly momentum changes. The net force equals change in momentum divided by the time interval. If we rearrange that relationship, we get this important statement. Net force times the time interval equals change in momentum. The quantity net force times time interval is called impulse. So impulse is equal to the change in momentum. This relationship is often called the impulse momentum theorem. It tells us that a force acting over a time interval changes an object's momentum. Impulse is a vector quantity. It has the same direction as the average net force, and it points in the direction of the change in momentum. The unit of impulse is Newton's second. This is equivalent to kilogram meter per second, which is same as the unit of momentum, because impulse equals change in momentum. A helpful way to think about this is the same change in momentum can happen with a large force over a short time or smaller force over a longer time. That is why padding, airbags, and follow through in sports matter. They change the time interval and therefore change the average force needed for a given momentum change. Let us apply this idea to a steel ball bouncing off a hard floor. A 0.2 kilogram steel ball is dropped straight down onto a hard horizontal floor and bounces straight up. The ball's speed just before impact is 10 meters per second in downward direction, and its speed just after impact is 10 meters per second upward. Part A asks for the magnitude of the impulse delivered to the floor by the steel ball. Part B asks for the average net force exerted on the ball during the collision if the ball remains in contact with the floor for 5 milliseconds. Before we solve it, we need a sign convention. Let upward be positive. That means the velocity before impact is negative 10 meters per second because the ball is moving downward. The velocity after impact is positive 10 meters per second because the ball is moving upward. This sign choice is very important. The ball does not simply go from speed 10 to speed 10. Its velocity changes direction. The change in velocity is from negative 10 to positive 10. So the total change is 20 meters per second upward. We should expect a fairly large average force because the collision time is very short, only 0.005 seconds. A short contact time means the same momentum change requires a large average force. Now let us calculate the impulse and the average net force. We are given the mass of the ball, zero point 0.2 kilograms, the initial velocity, negative 10 meters per second, final velocity, positive 10 meters per second, and also delta t is 5 milliseconds. So milli is 10 to the power minus 3. So this is 5 times 10 to the power minus 3 seconds. And that is 0.005 seconds. For part A, we use the impulse equals change in momentum. So the impulse is the net force multiplied with the time, and that is equals to change in momentum, which is mass times delta V, and then we can write this as mass times V final minus V initial, and then we can substitute the values. So we have 0.2 kilograms times 10 meters per second minus and negative 10 meters per second, and then this is equals to 4 Newton seconds. The question asks for the impulse delivered to the floor by the ball. By Newton's third law, the floor gives the ball an upward impulse and the ball gives the floor an equal magnitude impulse downward. Since the question asks for magnitude, the answer is 4 Newton seconds. For part B, average net force is impulse divided by the contact time. So the net force is equals delta P over delta T. In delta P we found 4 Newton seconds and delta T is given 0.005 seconds and we get 800 newtons. So this gives us 800 newtons upward for the average net force on the ball during the collision. This large value makes sense because the ball's momentum changes direction in a very short time. If the contact time were longer, the average net force would be smaller for the same change in momentum. The main takeaway is that impulse connects force and time to momentum change. A collision does not need a force that is constant. We can use the average net force and the contact time to find the overall change in momentum.